this project, and then especially to Dr. Dearden, who has served as my thesis chair. He has been incredibly supportive since the very beginning and has given me plenty of flexibility and freedom as I have explored a very diverse range of topics. Next, I wanted to thank Seth Glasser, who spent copious amounts of time editing this thing with me last week. But more importantly, he's been a sounding board for my ideas and my joys and my concerns throughout this project. Lastly, I wanted to thank Maggie and Julia for your financial support. Without further ado, here we go. So I ask you, what is going on in this picture? Well, it depends on who you ask. I'm sure everyone in this Zoom room, like myself, I'm sure we all have fond memories of this nostalgia of our calculus years. Believe me, not everyone feels this way about Riemann subdivision. I gave a presentation on an earlier version of this paper to a more general group with the School of Graduate Studies, and let me tell you, they were not as happy to see this picture. While some of us see a process that is intrinsically worthy of study, some people just get terrified. And it also depends on if you ask somebody who likes the idea of infinitely small objects, or somebody who doesn't. Of course, regardless of your style of mathematics, most likely you see these rectangles multiplying and shrinking in width and you imagine how they more and more resemble the area underneath this very nice curve, just like they taught us to in calculus. This is the limit concept, and there really is something undeniably valid about the limit concept. The limit concept was particularly advocated for in the history of the calculus and its conceptual development, the famous 1949 book by Carl Boyer. It will be seen that the kind of calculus most of us learned in college, henceforth called standard real analysis, it is not the only way that mathematicians take up in their approach to studying the real numbers. There are other interpretations about what is going on in this Riemann sum. What if we firmly stated that the end process of this Riemann partition was an infinite collection of infinitesimal rectangles, or even line segments without any width? This kind of crazy and yet quite old idea was the basic focus of my research. This practice, which historically came much earlier than the limit concept, was one practice that the arithmetization of analysis was condemning, and which Boyer frowns upon. In turn, the arithmetization of analysis and these views, which are espoused by Boyer, these are something that many contemporary mathematicians have reacted back at, especially in non-standard analysis. They are engaged in a radical return to more historical practices of geometric subdivision. Basically, the arithmetic idea is that all of the real number points exhausts the number line in a completed continuum. This is, for example, Dedekin's view, and it's known variously as the point set theoretical or the arithmetic view of the continuum. My discussion today is not about math history, so I'm going to brush over many of the details here. But basically, this school of thought admonished infinitesimal numbers, and they quite literally attempted to banish infinitesimals and our usual geometric intuition from the formalizations of analysis. And this is quite accurately described in this book by Carl Boyer. Boyer advocates for the limit concept and the arithmetic view of the continuum as a finalizing and resounding logical completion of the earlier quests in the development of analysis. In the 17th century, the use of infinitesimals in geometric derivations was very common, and it was in no small part because of the wild success of Bonaventura Cavalieri's 1635 book, Geometria Indivisibilibus Continuorum Nova Quadam Ratione Promota. After Cavalieri published his books, these types of methods led to the development of calculus. 350 years later, interest in Cavalieri's methods and the 17th century project has picked up again, and we will return to these more accurate interpretations later on. Even though Cavalieri's methods have generated interest, his techniques especially were taken by Boyer, and they were called arbitrary, ambiguous, logically inconsistent, naive. He said that they were doomed to failure, and worst of all, he said that they were based on geometrical intuition. If that sounds bad, you should have heard what Cantor had to say about the infinitesimals. Boyer certainly respected Cavalieri's work as an important precursor of the calculus, but clearly he felt that the analysis was better without any form of geometrical intuition, and that mathematics should be completely removed from anything external to pure logic. And they're not even wrong. You know, we mathematicians, we love pure logic. Myself especially. I'm a big Husserl fan, as a couple of you know. Anyways, Boyer supported a definition of real numbers as points or Dedekind cuts, and it was thought that the limit concept removes all of these bad things from the development of analysis in a miracle cure-all which provides a logically sound and predicative and indisputable basis for our approach to the real line. That sounds really nice, right? Why would anyone want to question that? Well, as it turns out, even though many in the 19th century and 20th century mathematics were attempting to banish intuition and the infinitesimals, they were retained, most notably in the practices of physics. They were just pushed a little bit further underground. Physicists were not waiting around for the mathematicians to tell them that their mathematics was sound. As has been noted several times in the literature, physicists and other practitioners of the physical sciences have long embraced these infinitely fine partitions. One basic premise of my thesis was therefore that geometric subdivision is a form of approximation that connects this system of analysis called NQA+ to deeper pursuits in the philosophy of science. Further, a special breed of numbers called the hyperrational numbers are a particularly elegant tool for developing models of ideal approximations to infinite precision. My goal today is to develop these two ideas and to show you how NQA+ has a system of integration that recovers our intuitive and approximate approach to Riemann sums in a manner consistent with the intuitive practices of science and, fascinatingly, certain interpretations of Cavalieri's indivisible methods. First, I will actually show you how infinitesimal methods are regularly used in physics. Right off the bat, let's take an example from classical fluid dynamics. Don't worry too much about the details of NQA+ yet. I will certainly be filling you in on those very, very soon. Just note that there are no limits in this following derivation. In physics, a laminar flow is a nice, uniform flow of fluid. It turns out that laminar flow is the normal condition for blood flow throughout most of the circulatory system. It is characterized by concentric layers of blood moving in parallel down the length of a blood vessel, as in the picture that you see here. Now, in NQA+, we define some important functions as integrals, such as most notably the arctangent function here. And as usual, we'll define pi to be 4 times arctan of 1. As the title of my project indicates, the actual development of this integral is actually a little bit tricky, but once we have it, we have a great approximate form for all of the trigonometric and exponential functions, and therefore we can approximate this hyperrational pi, which is crucial in the following proof. That's right, as we all know, a truly irrational pi is never actually used in the practice of concrete calculations. We wish to know the volumetric flux, or the volume of blood in a cross-section of the vessel in flow per unit time. We're going to let the blood vessel have radius r, and we're going to let v denote the velocity of the blood at distance r from the center. Denote QRS as the volumetric flux of the annulus from distance r to distance s, and we're going to calculate Q from 0 to r, which is the whole flux of the blood vessel. We assume that Q is additive, and therefore it satisfies our intuitive criteria for a volume function. We define ARS to be the surface area of the annulus from r to s at the cross-section, and we assume that A is additive as well. Notice that the area for this annulus is known, and it's given by this formula. We can rewrite it as follows. And here we are. We are considering the surface area of an annulus with infinitesimal surface area. And notice that there's now a dr and a dr squared term. This is going to make the hair on every physicist's neck just stand right up. We know that we're going to neglect this dr squared terms. In classical analysis, this is considered to be one of those mathematically unrigorous habits that physicists operate by. But in contemporary non-standard analysis, this framework has been developed quite extensively, most notably by Karol Hrabatchik, and we will demonstrate this in the following derivations. Denote 1 over dr by alpha. Then dr is not alpha infinitesimal, and this is kind of a technical definition, doesn't really matter. Dr squared is alpha infinitesimal. However, it's not alpha squared infinitesimal. In Hrabatchik's stratified framework for analysis, dr squared is called ultra small relative to dr. In this way, we refine the usual finite versus infinite dichotomy of standard and non-standard analysis, and we justify the intuitive practices of the physicists. Many results don't require stratified tools, and so we usually just state our result with the usual approx sign, but just know that this is always lurking in the background. So, restating our above result, we know that dr is not alpha infinitesimal, and therefore we can say that the area is pi dr squared is infinitesimal relative to 1 over dr. And thus the area of the annulus from little r to r plus dr is 2 pi r times dr. Notice that this is an infinitesimal circumference of a circle. Talk about geometrical intuition, huh? Also, notice that this calculation is in accordance with the long-standing practical tradition of engineers, where squares of infinitesimals and higher degrees are literally negligible in calculations. However, the infinitesimals are rigorously cataloged here, and there's nothing happening that is outside of the axioms. Finally, I'm going to go pretty quickly through the rest of this derivation. As expressed in the diagram, we see that the velocity is decreasing as the length gets larger away from the center. Thus, the max velocity on any annulus is the inside, and the blood flows slowest towards the outside. Next, we're going to apply a classic technique of physics that uses infinitesimals. We are going to define the flux Q to be the product of the instantaneous velocity times the surface area. We're going to take the flux, we're going to use known results about the velocity, and we have this inequality which bounds the flux by the two velocities times surface area. However, the velocity for laminar flow is known by Poiseuille's law. If the blood pressure is P, the viscosity is eta, the length of the cross section that we're considering is L, we're going to denote K by P over 4 eta L, and finally we have Poiseuille's law. The velocity of the blood is K times big R squared minus little r squared. Therefore, we use Poiseuille's law to find the velocity at little r plus dr. We arrange it in terms of the velocity at r, we multiply by our area function 2 pi r dr, and then take a look here. There's a dr squared term and a dr cubed term on the right. And therefore, we know that this approximation is 2 pi r dr times the velocity relative to dr. We recall our inequality about the flux from 0 to r, and since the two outside terms are infinitely close, we know that the flux is going to be infinitely close to both of them. Therefore, we have an approximation for our flux based on area and velocity. Lastly, we just have to do a little math, and we're going to take the sum of a bunch of these really thin little annuli. This is the crucial step for our system of integration. We are going to chop this blood vessel up into a collection of infinitesimal rings and take the sum of all of them. With the partition here, we're basically holding up an infinitesimal ruler up to this blood vessel in an idealization of actual practices of measurement. Since the function Q is additive, we can take this non-standard Riemann sum over all of the subintervals and derive a definite integral. The intermediate steps here are pretty technical, so we're not going to worry too much about them. But we have at the end an empirically verified formula for the volumetric flux of a blood vessel, which we derived using infinitesimal numbers in a strict framework for non-standard analysis. It's pretty amazing to think that some process like this could ever be made into a rigorous system in a mathematically useful way, but it has. Many of you, like me, are probably not terribly familiar with what the physicists are doing. So hopefully this example cleared things up a little bit and fascinated you with its use of infinitesimals. Next, I'm going to tell you a little bit more about NQA+, so that we can see how this system for describing the intuitive practices of mathematics in physics is actually turned into a system for analysis. So here are the creators of NQA+. Patrick Suppies is from Stanford. Rolando Chuacui was from Chile. It's always nice to have an idea about who you're talking about. Chuacui died as soon as NQA+ was created, and that's actually pretty amazing for me to think about. Suppies continued to work on it in a slightly different form. And here's the basic story. In the early 90s, when NQA+ was being developed, the math that was being used in physics textbooks looked nothing like the math that was appearing in textbooks for analysis, even in the most constructive settings. The proof of laminar flow is a great example from classical physics. Let's just say that the theoretical physics and the quantum physics was even further removed. Well, Suppies and Chuacui said that in the physics texts, there is basically no use of quantifiers. There's really not any existential proof systematically. There's not really any use of negation, and there's a positive and overall computational character for the physics textbooks. There's an extremely constructive approach to the theoretical developments, and lastly, there is indeed free use of infinitesimals, and they don't care about foundational concerns in that regard. This is quite contrary to the texts in real analysis, right? And NQA+ was developed to try to match these characteristics. To that end, the authors proposed NQA+ as a system of constructive non-standard analysis, which would be finitarily consistent, and that would actually formalize the intuitive approach to math, which is taken by scientists. So, in the rest of this presentation, we will simply develop some of the powerful and philosophically interesting techniques of this system, and at the end, I'll make some concluding remarks about my actual research project and results. Along the way, we'll have a crash course on a couple of fantastic tools from non-standard analysis, which will help distinguish non-standard analysis from NQA+. You know, NQA+, it doesn't actually stand for anything. In my imagination, I think it stands for non-standard rational analysis, where the Q is for the rational numbers, but I don't actually know that for sure. I don't want to write that in stone. The plus, however, I know. The plus has a technical meaning. In fact, the original authors of the system didn't even name it NQA+. They just sort of did it without a name. The name came later. Now, we'll take a big step back and just take a look at square one, the axioms. Like a lot of other systems, it's easiest if we just assume that 0 is a natural. And yes, every natural number has a successor. We have a weak form of induction and a minimum principle, that's the thing on the bottom there. We have this minimum principle which allows us to find the least something in a given set of somethings. So we have the hypernatural numbers, but that is not all. We can manipulate them with field axioms, and therefore we have all the hyperintegers and the resulting quotients, which we'll call hyperrational numbers. Instead of asserting completeness axioms to build the real numbers, we take a different approach. And we're going to postulate an infinite natural number, which we call nu. We call the inverses of these infinite numbers infinitesimals. And any finite number, and most importantly, they have some axioms too. Anything smaller than an infinitesimal is infinitesimal. Any number, any finite number times an infinitesimal is an infinitesimal. And any formula which involves the predicate inf, or the approx symbol, is called an external formula. And we want to make sure that the hyperrationals are an Archimedean field, but not in the standard sense. It is hyper-Archimedean. Further, the hyperrationals are not a complete field like the reals. Square root of 2 is real, and it's in the completion of the rationals, but it is not a hyperrational. The hyperrationals are called the enlargement of the rationals. As we will see next, the best we can do is approximate square root 2 infinitely closely by the hyperrationals. Actually, I'd like to show you how any real number can be approximated infinitely closely on the hyperfinite grid. The hyperfinite grid embodies the infinitesimal mesh. And H. Jerome Kiesler, he's a monumental scholar in non-standard analysis. He says that one of the most important features of the hyperreal line is that each interval can be partitioned into hyperfinitely many intervals of the same length. This feature is captured by the notion of a hyperfinite grid. It is a fact of non-standard analysis that hyperfinite sets enjoy exactly the same properties as finite sets. Every hyperfinite set is discrete. Every set has a least and a greatest element, and every element has a successor. Therefore, we're going to denote some positive infinite hypernatural H and construct a hyperfinite grid as the hyperfinite set of all multiples of 1 over h between negative h and h. It's a subset of the hyperrationals, and it bounds the standard reals, as in Kiesler's diagram here. He often used optical technology as a metaphor for what non-standard models were accomplishing. It's just another way of modeling stratification. This grid will become the foundation for almost all of the proofs in NQA+, as well as the definite integral. Now, what we need to prove is that any real number can be approximated infinitely closely on the hyperfinite grid, regardless of our choice of infinite h. In order to do so, we need a basic tool from non-standard analysis called the transfer principle. The basic historical motivation behind the transfer principle is Leibniz's old idea that infinite objects are ideal fictions which must obey the same rules as finite objects. Indeed, Robert Goldblatt expressed this idea in a universal form and an existential form, as you see here. In the universal form, we know that if a property holds for all the real numbers, then it must hold for all the hyperreal numbers. In the existential form, we know that if there is a hyperreal number satisfying a certain property, then there exists a real number with this property. We're going to take well-formed formulas and transfer them with the star map, which quite literally will put stars on everything in a certain way. Yes, very pretty math stuff. The big picture comment here is that transfer is the way we move things from the world of standard objects to the world of non-standard objects, where we have lots of nice rules and we can manipulate them with basic algebra. Now we're going to return to our proof that any standard real x is approximated by an element on the grid. In our diagram here, we see that the line is partitioned by equally spaced nodes with mesh 1 over h. We are looking for the closest node. Note that for any given real number x, the set of all multiples of 1 over n less than or equal to x has a greatest element for every n of the natural numbers, the standard natural numbers. By transfer, we have that the set of all multiples of 1 over n less than or equal to x has a greatest element for every hypernatural n. Therefore, one of our hypernaturals, big H, has a greatest element on the grid, and we're going to call that one k sub h. It bounds x on either side on the grid. Notice that if we just had a minimum function for hyperfinite sets, we could do all this in one step. And you just define it as the greatest node after x, take away 1. This type of methodology will come back with major force in NQA+, as we will see. I would further like to mention that this proof is indeed constructive, as this inequality is a well-known algorithm for approximating any rational number by an integer reciprocal. However, in regular non-standard analysis, we can go even one step further. One step too far, you might say. We have a special map that takes our approximation on the grid and maps it directly to the standard number x which it's approximating. Remember, we took these objects and approximated them with hyperfinite sets using the transfer principle, and now we're going to bring them back down to the standard world using a similar principle called the standard part map. I'll briefly tell you about the halo of a real number. In starred R, the infinitesimals, all of the hyperreal numbers infinitely close to 0, are the only numbers infinitely close to 0. They're the only ones. The halos form equivalence classes around each hyperreal number. And so in the end, we can define a map which takes every finite hyperreal to its nearest real number neighbor, or standard part. In the end, we take our objects from the non-standard world and bring them back to their standard neighbors with the standard part map. In our last example, x is the standard part of k sub h over h. Oddly enough, the key difference between NQA+ and non-standard analysis is simply that NQA+ does not have a standard part map. As it turns out, the standard part map is equivalent to Dedekind completeness of the real line. This is a sort of surprising result, actually, and one of the basic premises of NQA+ is that completeness of the real line is not assumed, and therefore a standard part principle is not even available. One quote by the authors that I investigated extensively was this quote. Part of the point of NQA+ is its use in showing that mathematics carried out for scientific purposes does not rely on the existence of a completed continuum. The structure of the hyperrationals alone is rich enough to carry out such mathematics. Standard definitions of continuity, differentiability, and other notions from analysis rely in an essential way on the existence of a completed continuum. Standard analysis takes as basic a completeness axiom such as the least upper bound principle. On the other hand, the corresponding definitions in non-standard analysis do not rely on such principles. By trading in the completeness axioms and the standard part map for axioms asserting the existence of infinitesimals, we end up with a system that is actually more constructive, and in many ways it better matches certain geometric intuitions about the number line. Well, in order to show you how these constructions are actually used in NQA+, I will prove a basic theorem for continuous functions before talking about integration. One of the results I prove in NQA+ is the approximate intermediate value theorem, which demonstrates this crucial difference in other features of the system. For example, that handy minimum function that I showed you earlier. It's a very beautiful proof and it's fun to see, I promise. However, it's about to get quite a bit more technical, and I'm going to be moving a lot faster. I have to appease my advisors, and there isn't going to be enough room for pretty pictures and stuff anymore. First, I need to tell you about functions and how they are defined in NQA+. The way we will work with functions is through the hyperfinite partition, what we call a geometric subdivision. From now on, we define an infinitesimal mesh, du, and define the nodes of the subdivision by u sub I. The collections of u sub i's form a partition of the closed interval of order nu. We have to precisely state what it means for a function to be defined on a closed interval a to b. In NQA+, a function requires a defining formula, phi, which depends on a few parameters. So when we talk about the domain of f, in the future it's being used as an informal shorthand label for this sort of abstruse formula. This is Soupy's at his finest, I promise. Anyways, for f to be a function on a to b, it has to satisfy three criteria. There must be a finite set of bounds, a1, b1, such that for any point in between the bounds, this formula holds. F sub dom has to be monotone and Lipschitz continuous on the bounding interval, and this is for technical reasons. And lastly, we need F sub dom to be injective on the bounding interval. F sub dom is a kind of tricky term that is heavily tied up with what the inverse of a function is. Lastly, once you have a function defined on an interval with a geometric subdivision for that interval, we're going to define a selector for f and u on the interval. It's called zeta, and so if you wanted to, you could call it the z-lector if you wanted to, but that's a personal preference. It is defined on all the hypernaturals, and f has a value on each zeta sub I. That is, just because a point on AB satisfies the formula for being in the domain of a function, it doesn't mean that it does us any good on our subdivision. We just don't have the set theoretical strength in NQA+ to take any point on a subdivision when we're integrating. For those that know Riemann integration already, this notion of the selector is very much related to the tags that we normally put on a Riemann sum, like a left Riemann sum or a right Riemann sum or whatever, but we are generalizing this into a more useful tool. So we can informally say that the selector is an embedding that takes each subdivision of the domain to a subdivision of the pre-interval, like a tag. It's kind of hard to explain, and it's a construction that is used in all the proofs. Okay, I lied. Here's a picture. It's from the original NQA+ document, which describes the selector. You can see each node of the subdivision of the pre-interval is mapped to the interval AB at hyperfinitely many points. And exactly one of these points is selected on each of the subintervals U. Actually, it's always the first one, as you can see here. The way the selector does this is quite complicated, and in my paper I spend quite a bit of time proving its intricate details. Unfortunately, I just don't have the time to tell you about how it actually works. It's very important. Maybe you will ask me about it later. Looking at you, Seth. Instead, I will show you how it is used in NQA+. First, we have a non-standard form for continuity. Then, our carefully constructed functions. For our carefully constructed functions, we can say that for any number between the endpoints of the interval AB, there's approximately one equal point on a subdivision nearby where the function is actually defined. That is, we will literally take the least selector at or after x. And there's that minimum function I told you about right there. Basically, we're just adapting that proof for approximation on the hyperfinite grid and making it our go-to methodology for this restricted form of quantification over subdivisions. Now, the proof of the intermediate value theorem is actually very similar to the previous theorem, and it's based off the same concept. But instead of being given any x on the domain of f and finding an approximate nearby selector on the subdivision, we're given a continuous function which crosses the x-axis on a given interval, and we're going to show that there's a selector point somewhere on the interval whose function value is approximately 0. Let's go over this proof. We're going to designate n as the first subdivision whose selector value is greater than 0. Yes, no kidding. This is allowed according to our hyperfinite methodology. And it really is an effective way of tackling these problems. Suppose, without loss of generality, that the selector at n lies off of the endpoints. Then its predecessor index is at least 0. By definition of the min function, we know that the selector values will straddle 0 on either side, but we also know by construction that they are infinitely close to each other. And since f is a continuous function, their function values are infinitely close too. This means that the function value of zeta n is approximately 0, as desired. As you can see, just like with the blood example from earlier, we've held up an infinitesimal ruler to our continuous structure. If we imagine that these ticks on the ruler are infinitely close, to our naked eye it looks just like the continuous interval, and for all practical purposes they are the same. In fact, we may not have any feasible way to empirically distinguish between the two concepts. This proof of IVT approx actually wraps up the first part of my presentation. And it ties a lot of the stuff together that we have seen already. Well, first off, anyone who's ever worked with a step size or a grid mesh or even the Newton-Raphson method from numerical analysis, you know that what we just did was actually a really easy kind of approximation. We just had to find where our subdivision selectors crossed the x-axis with the built-in minimum axiom for hyperfinite sets. Basically, we just iterate one node after the next. It is derived exactly from the transferred process of approximating on a finite grid, which we saw in Kiesler's proof with the transfer principle. And it's pretty amazing, but this will be bootstrapped into an entire theory of integration, and it's beautiful in its simplicity. And it actually accords well with the scientific practices, as we have already mentioned. In the proof of IVT approx, we get a taste of how NQA plus reduces most problems in analysis to finding a subdivision, finding an algorithm for the selector based off of some data, and finding an algorithm for min or max. The data in this case would be points in the domain of a function at ideally available infinitesimal levels. The approximate nature of these results is due to the approximate nature of our data and to the and to the restricted kinds of inferences which we can make. At many different levels, the approach of NQA Plus was designed to match the practices of the physical sciences. These types of approximate results led the authors to claim in 1997 that with NQA Plus and ERNA, we can literally create models of analysis which allow us to dispense with the continuum in mathematical practice, because the continuum is not even verifiable empirically. There is no experiment which can distinguish between phenomena being discrete or continuous at a fine enough level. Now, I'm sure that thought will linger with you. Sometimes I just think about how far apart atoms are from each other, and I just sort of can't sleep at night. But I don't want to give you any nightmares about continuity, okay? We've just gotten to the main event of my presentation. We are going to assume that the selector and the subdivision concept will play in really nicely into our integration theory and just jump right into the good stuff, okay? After I introduce the NQA plus integral, we will take a look at what the authors mean when they say that it accurately reflects our geometric intuition of the number line. From the same techniques as those we used in the proof of the intermediate value theorem, plus a few specific notations for summation, we can derive an integral for NQA+. Basically, we will be taking the hyperfinite sum of infinitesimal rectangles as an approximate integral. The length of the rectangles is our mesh, and the height of each rectangle is determined by the function value of the selector. Notice this slightly non-standard notation in front of you, where the sum notation indicates that we are summing the rectangles from the point A to the point B. Of course, in real analysis, this sort of notation is never allowed. You can't just sum over a continuous object. Remember that idea too. This is going to be critical in the end. Our next task is to turn these non-standard Riemann sums into an integral. That is, the actual area underneath a curve. We will say that a function is integrable if all of its non-standard Riemann sums are approximately equal, regardless of the infinitesimal mesh we use. A later theorem will prove that, in fact, every continuous function is integrable, and its integral is approximately equal to its non-standard Riemann sum. Some authors define this sum and the integral to actually be equal, but I think it's much prettier and probably more accurate to define them at equality up to infinitesimals. Okay, there's a lot more we could say about the geometry and the philosophical significance of this construction, and believe me when I say that I just wrote a thesis about it. Okay, I have chosen to talk to you today about just one of these very interesting facts. In the original papers, Suppies mentions several times that all of these scientifically interesting structures are actually deeply connected to 17th century geometry, and he actually mentions Cavalieri by name at least 3 times. So I went in and I wrote a chapter about those remarks. This type of integration is just the intuitive approximation of surfaces by infinitesimal rectangles, as in this picture of the Riemann sum which we saw at the beginning. This type of reasoning was exactly the kind of infinitesimal, intuitive stuff that so many mathematicians have disapproved of. Boyer would have been astounded that we would adopt such a backward methodology as our entire foundation. But here's the best part, and one of my main results. I claim that Boyer himself facilitated this interpretation of the integral. To understand this claim, we have to see how Boyer interprets the work of the 17th century geometer Bonaventura Cavalieri. Briefly, let's just take a look at how Cavalieri actually anticipated this certain very important integral. This mathematical transcription I'm going to give you has been carefully recorded according to Cavalieri's actual texts. We will see that they are different than how Cavalieri's methods are usually remembered, even if it's kind of a subtle difference. In this example, we can see in the figure that Cavalieri would not just traverse 2-dimensional figures with lines, but he would imagine each line of a figure making a square, and he would deduce results about these ratios. In this example, we will see that he anticipated the result of integrating t squared, which, as we all know, is an exquisitely important integral. I used it this morning, actually. He was one of the first people to find this result. Basically, we're going to take this rhombus. In the bottom corner here, we're going to take its diagonal, BD, and we're going to cross it with the bisector from M to N. Then we traverse it with this tangent line, PS. Cavalieri imagined this crossing tangent line PS starting at the top of the figure and then moving all the way down, and each intersection with the figure would form all of its lines. But further, we would imagine all of the lines squared according to their given length at any given point of the figure, like in the little planes from the picture above. In this notation, the O stands for omnes lineae, which is Latin for all the lines. And with the little black square there, we're basically saying that we're taking all of the square lines of the figure, okay? This is an accurate translation of what he was doing, and even though he tended to be quite difficult to read, and he wrote in Latin and whatever, it's good. In the end, he deduced some certain ratios about the entire figure, all these intricate results, and then according to the previous formulas, he arrived at the result that all the square lines of the entire figure, which is the cube formed by the base, DC, it had 3 times as many square lines as the half triangle BCD. That's what this integral transcription means here, when you interpret it geometrically. We will see that if you interpret it analytically, these results can be found in a different way, and there's a very interesting difference. If you start at the bottom corner with C there, and you traverse all the square lines from the half triangle to the point B, from the right side to the diagonal, then you have a square pyramid, right? And the cube is formed by the square at the base. Boyer criticizes Cavalieri's proof for being stated in a confusingly verbose geometrical terminology, and he offers this following summary using notation from summation. He follows Cavalieri's ratios, and these actually are correct. They follow Cavalieri's ideas. And then next, Boyer simply followed the traditional Cavalieri interpretation and said, yes, this figure is the sum of all of its indivisible parts, even though Cavalieri never asserted such views. In fact, he asserted quite the opposite. So Boyer says, why don't we just take the sum over all these lines? And then I ask you all in the audience, where have we seen this notation before? Boyer, Mr. Rigger himself, he's summing from the endpoint of the line M to the endpoint N, just like we said it's something Boyer wouldn't do. Clearly, he doesn't think that Cavalieri's ideas are quite rigorous, so, what does it matter if we let a little intuition slip in, since we're just going to fix this later on with limits anyways. No harm, no foul. But we fill in a couple more substitutions, and finally, we get the same result, except stated in summation notation. This basically looks like a result stated in NQA+, and I claim it actually might be. It's very likely that Pat Suppies was familiar with Boyer's writings on Cavalieri. Not that he was intentionally matching this particular transcription or anything. This type of summation notation is actually common in non-standard analysis, but it's a very interesting philosophical gesture. These were the sort of integrals that Boyer disapproved of, and they are exactly the integrals that we have based our entire system of analysis on. And not only that, but Boyer was the one who wrote them down. So, as I conclude, I'll speak a little bit more about why this was possible. One of Cavalieri's colleagues, and a student of his named Evangelista Torricelli, he was one of the first to popularize this idea that the figure F was actually the sum of all of its lines. As Kirsty Anderson, a Cavalieri scholar, points out, this idea of a sum would have been unknown to Cavalieri, and that he never actually equated the figures with the collection of all of its lines. He explicitly wrote this down, although he was so happy that Torricelli liked his ideas that he never seemed to say anything about it. Torricelli was very good, by the way. Did some great stuff. The idea of all the lines as a sum began with Torricelli, and it magnified throughout the 17th century when indivisible methods exploded into the calculus. So, in my research, I asked 3 basic questions. The first one, I've talked at length about it, that's how NQA+ develops geometric subdivision into a theory of integration. I don't need to say anything else about that. The second question was, what practices are Chouakwi and Suppies referring to when they talk about geometric subdivision? Well, clearly they are talking about the non-standard techniques of hyperfinite approximation, which we talked about above. Further, Suppies references Cavalieri several times when he talks about NQA+, but when we actually examine these remarks, it appears that he's retaining the sum interpretation that Boyer used specifically. This is a fascinating reversal of the project of arithmetization, and very interesting to find it within Boyer's own work. Finally, my last research question was, what are their motivations for using geometric subdivision and integration? NQA+ was developed in light of the very possible fact that there will never be an empirical validation of the existence of the continuum. It therefore seems that geometric subdivision is a form of approximation that connects this system of analysis to deeper pursuits in the philosophy of science. Okay, there are many questions that I have for these authors. Perhaps you have a question or two you would like to add on to my pile. Thank you all for listening, and thank you all for helping me through this. I am excited to hear what you enjoyed about my presentation. I'm done talking now.
Can you pronounce the name of Cavalieri's book one more time?
Geometria indivisibilibus rationa quadam nova. Oh, the last word slipped me.
Right.
I'm looking for it, though. I'll get it for you.